So yeah, and first I'm going to do, I'm going to change notation. I change my mind a little bit. You know, the star of the show really should be something I'm going to call dep k e, the dependent sets of k vectors in E. And this is a subset of the direct sum of k copies of E. And this is the subspace of k tuples so that that collection is dependent. And then, because this wasn't a smooth object last time, we defined something, and I called this dk hat last time. I'm just calling it dep k, and the hat is going to go up top. So sorry for the change in roles. And all this is going to be a direct sum of canonical k-1 plane bundles in E. And so how can I think of this? So this is, again, essentially by definition, the space of k-1 dimensional subspaces of a fiber of E, right? So that's the fiber of E is the vector space. I'm looking at k-1 dimensional subspaces. We topologize that as we did last time, and then k points on that subspace. And of course, if I have k points on a k-1 dimensional object, that is going to be a dependent set. And so there's a map this way. The other way I want to think about this, by the way, this is more conceptual, but it's the space of k dependent vectors in E and a witness and a choice of how they're dependent through that k-1 dimensional subspace. So this is just sort of the idea. The rigorous definitions are there. And so what we do is define, so if E is rank n, fibers are n-dimensional, then we can define, we set that Wn minus k is a natural grading of E is the chromology class represented by the tome cochain of these k-dependent things, but the smooth version mapping to E, sorry, not to E, but the direct sum of k copies of E. And so that's in H, the claim is n minus k of this direct sum. Of course, this direct sum is a bundle, a vector bundle over M, and any vector bundle is homotopy equivalent to its base. So we can identify that with the cohomology of M, and everything is mod 2 coefficients. Let me, maybe I'll emphasize that for the moment, but you'll have to pardon me if I drop it later. So, right, and so the thing is, what we can do is this this equivalence. What we can, what this equivalence is, well, we know in one direction we have a chosen projection for the bundle. In the other direction, which is what we need to map from the cohomology of the total space of direct sum of k copies of E to the cohomology of M, we need to map the other way. So one thing we can do is we can use, well, any map in the other direction, but the direct sum of sections of the bundle. That's the most natural thing to say. So these are like, if it were the tangent bundle, for example, this would be k different vector fields. So imagine on the two sphere, a couple different vector fields, or on an n-dimensional manifold, you've got all those different ones. And so, right. So here's the main thing to know about these classes. Here's their identity, really. The way we're going to put it is that this obstructs the existence of k linearly dependent sections. Sorry, linearly independent sections. Let me emphasize pointwise everywhere. Not linearly independent as in, you know, they're independent somewhere, but no, they're honestly everywhere independent sections. Okay, let me give the proof and then a little bit more about the meaning. Although again, so one of the first things to say is if k equals w minus k, I knew I should have done this. This should be minus k plus 1, right? And so should, yeah, so that's the definition. There's also a plus 1 here and a plus 1 here. And a plus 1 here. Because if k is 1, the obstruction to a linearly independent section is just the obstruction to a non-zero section, and that's the Euler class. And that's Wn is its mod 2 reduction. The Euler class, it's mod 2 reduction when the Euler class is for an oriented bundle. Let me just say a little exercise. We'll say this again later, is to check that the dimensions will work correctly here. Right. So the point is that if you know, if I've got our independent sections, then, well, let's go back. Let's realize that this map factors through dep k. And so its image is exactly dep k. This is surjective. So if those are independent sections, then the pullback of dep k hat to M via these sections is empty. Because by definition, that direct sum of sections isn't going to intersect dep k, which is the image of dep k hat. And so, yeah, so that pullback is empty. And so that means that this class is 0. Okay. So normally in obstruction theory, by the way, that's the proof basically, but let's just note that the contrapositive is that if this class is not 0, that means that there's no such collection of sigma I, which are independent everywhere. Okay, so such sections do not exist. Right. So that's really the identity of these Stiefel-Whitney classes. They obstruct independence of sections. We'll see that there's other approaches to characteristic classes. There's other ways to associate numbers to vector bundles, which measure them cohomologically, naturally, etc. But this is by far the slickest, the nicest way, as we'll talk about at the end of this lecture, for the axioms that they satisfy. Let me say a little bit more here about this obstruction. So in general, we can consider the pullback, not just when this is empty, but this pullback as representing our class Wn minus k plus 1. So that's just another manifold mapping now to M. Sometimes it'll be a submanifold, sometimes not if M is very high dimension. I mean, the point is that, yeah, well, let me do those technicalities a little bit, but the point is that on the chain cochain level, we really, so in fact, you can really think in terms of dep k. So in fact, I claim, but I won't prove for you, and we're trying to avoid this. In fact, wrote the same thing. This works as a cochain, but it is singular. But I didn't want to develop tome cochains for singular objects. So yeah, so the point is that once you consider them as a cochain, they're fairly interchangeable. So let me talk about such technicalities a little bit. Okay, so to clarify some technicalities before we get to the axioms. So first of all, for mod 2 chromology, what we just did, I don't know if you noticed, is we didn't talk about this dep k hat as embedded in something and then mapping. For mod 2 cohomology, we can dispense with the embedding, and a tome cochain is just is essentially just some manifold mapping to M properly. And let me sort of say a little bit more about why. So the point is to some map from delta n into the base, we associate the count mod 2 of the pullback of W. And what is the pullback of W? It's the subset of delta n cross W of T cross little w, so that sigma of T is f of W. And another way to say that, if you're not that versant with pullbacks, I find it helpful to think of that as sigma cross f, the sigma cross f preimage of the diagonal. Right, the fact that sigma of T vector is equal to f of W means that their images sit on the diagonal. And if you think about it, and of course this we claim only makes sense with n plus the dimension of W equals the dimension of M. And here, if you keep track a little bit, this is the codimension of this is the same as the dimension of M, but sigma cross F, its domain, has dimension, well, it's n plus the dimension of W, which is dimension of M. So again, we see that the preimage is going to be this codimension 0 subspace of delta n, sorry, codimension n subspace, sorry, codimension equal to the dimension of M subspace of delta n cross W. And so it's going to be a 0 manifold. So that's how pullbacks work in general. And here all we need is the map F. The embedding is important when we do oriented objects or co-oriented objects. The embedding really just makes those choreo orientations consistent. If we don't have that embedding, we could try to assign pluses and minuses to various intersection points. By the way, transversality here means that you know, there's not a lot of room for play here. Delta n and W have just enough tangent vectors to span the tangent space of M. That means that any place in the pullback, in this case, both of them have to be immersions. Well, if they're both immersions, then you know you've got some normal bundles around. But if the map F is singular, I don't know of a good way to make those consistent other than with this ambient embedding. So again, for the mod 2 theory, we just have this map. That's what we've given ourselves. We'll come back to co-orientations later when we do like Turing classes, that kind of thing. What else do we want to say? So an important point to note is that f, for example, could be constant here. And you'd say, well, there's no way that could do much for you. And in fact, then the only way for sigma to be transverse to f is for sigma to avoid that point in the image of f. So there's this interplay. We're allowing ourselves highly singular maps, but the singular maps don't impact things. So in fact, we want to say that in general, Sarg's theorem implies that, let's see, let me, so given f, let sigma f, the singular set, be the, which is smooth, let sigma f be the place where the derivative is less than full rank. So then Sarg's theorem says that the image of sigma f is measure 0. And so so if you then think about in this setting with delta n and w of complementary dimension, so that implies since pullback is locally intersection, so delta n w of complementary dimension implies, first of all, that pullback, transverse pullback equals intersection at places where there are immersions, but then our Sarg's theorem, so then the image of sigma f can be avoided. And that really says that for these purposes, our dep k and dep k hat at the level of cochains will give the same theory if we had a theory that really rigorously treated dep k, which we don't. But I wanted to say that it's no. Conceptually, you're in solid footing, and if we wanted to develop singularities, you could use dep k instead of dep k hat. Right, but let me do say that that's because we're in complementary dimension. So here's a little exercise, just so you kind of understand how these ideas work more generally. Give an example, construct an example, necessarily not of complementary dimension by what I just said, of a pullback of some non-injective which is transverse, and therefore, so by some, instead of sigma, let me give you some more flexibility. Take any v you want, which is transverse and smooth, but for which the image of G does intersect the image of the singular set. Okay. There's lots in nature, but again, you want to now, instead of V of complementary dimension to W, V is larger dimension. Eventually, it's got enough dimensions so that even though we sort of pick up too many dimensions in the preimages of singular points for F, it sort of all works out. We have some smooth objects. So there's fairly simple examples to make, but I want you to, if you haven't done the differential topology, just play around with that. We're not going to use that, I don't think, but just so you understand the extent of the definitions, even though what I just said is for these complementary dimensions, you can really think about the singular dep K and its preimages and that kind of thing. Okay, so axioms for characteristic classes. So theorem, the classes WIE satisfy. Maybe in some cases this will need to be a definition, and these are the Milnor and Stasheff axioms with their numberings. Axiom number 1, well, so WIE is an HI. And W0E is always 1 in H0. Oh, and of course they're in the chromology of E, but let's just have a base M. And WIE is 0 if I is bigger than the rank of E. I'm going to ask you to verify these axioms, and I'll let you determine whether it's immediate from extending our definitions or just something that needs to be imposed. So this is a kind of a funny axiom from that point of view, set of axioms from that point of view. Right now, we just haven't defined them. The definitions don't make sense, but maybe we can extend the definitions for which, in a way in which this, we can verify these. Number 2, these are natural. So WI of a pullback of E is the pullback in cohomology of WIE. Three is the most important axiom. If I have a direct sum, then there's a formula. This is a K. Then there's a formula for the characteristic classes of the direct sum in terms of the characteristic classes of the individual bundles which made the direct sum. This is called the Whitney sum formula. I'll put their names to the right. So this is naturality. This is called the Whitney sum. And finally, kind of a funny axiom, but keeps it from being trivial, defining, for example, WI to be 0 unless I is 0, in which case it's 1. That would give this theory unless, until you say that W1 of this tautological bundle for just V equals R2 is not 0. So this is a bundle over P1. It's the Mobius bundle. So let's just call this normalization or something like that. And these are I don't know, these are sort of degree axioms, degree constraints. or just degree. So we've got the degree axiom, naturality, Whitney's sum, and a normalization saying that this theory isn't trivial. So there we have it. And it turns out that, and the next lecture will show, we'll play around and see that these axioms let you make some pretty remarkable calculations from the get-go. They distill a lot of information. Again, for me, the workhorse is the third axiom, Whitney's sum. That's also going to be the hardest to verify. At the moment, let me just give it as an exercise for you to verify the easy ones. 1 and 2 and 4. The powers of 2 are easy. Other things are not. That's happens elsewhere in life. Yeah, and again, for 1, that might involve making a definition or extending our definitions in some ways. It's not that important. 2 and 4 are, I think, shouldn't be too hard for you using what we've done. And then let me give one other exercise, and then we'll call it a day and come back to axioms and their consequences next time. Verify that, so let, say, epsilon n be the bundle M cross R n. Pretty sure that's the notation Milner and Stasheff use. Then Wi, each of these Wi's of E plus epsilon n is the same as Wi of E. So I want you to verify this both from the axioms and from our definition. And if it's Wi, then what we want is dep n minus I plus 1 or minus 1. Yikes. I'll just say dep for now. Sorry, I didn't prepare that. Dep and dep hat if we want. Okay, so those are some exercises. Get started familiarizing ourselves with these axioms. Verify the easy ones. We're going to put off the verification of Whitney's sum, the most important axiom, until we see how much fun it is to use it. Then we're going to be motivated to prove it and do some, in our setting, some hard work to